Hello students, welcome to another video of number theory. Today we are going to discuss the fourth chapter, some functions of number theory. Number theory, chapter number 4, some functions of number theory. Some functions of number theory. Some functions of number theory. So first of all, in this chapter we are going to discuss the greatest integer function. Greatest integer function. In the third chapter, we have seen the theorem of legendary symbol of a and p is equals to minus 1 to the power n, where n is just the summation of greatest integer function of j by p. That theorem, before that theorem, we have seen the definition of greatest integer function. So first of all, the definition of greatest integer function is, let x belongs to R. Here notation real number. So first of all, in the number theory, the notation of real number comes. So let x belongs to R be a real number. Be a real number. Then this notation, greatest integer function of x or integral part of x, denotes the greatest integer function, greatest integer. This number denotes the greatest integer less than or equals to x, less than or equals to or equal to x, and we can read this notation as integral part of x. Integral part of x means the part of x which is integer, greatest integer less than or equals to this x. For example, suppose first example is for x is equals to 7.2, x is equals to 7.2, then integral part of x, that is integral part of 7.2, is greatest integer less than or equals to this number. So greatest integer which is less than or equals to 7. Equals to condition is for if x is itself a integer. Suppose if this x is equals to 10, then integral part of 10, that is greatest integer less than. So integers less than 10 are 1, 2, 3, 4, 6, 7, 8, 9. These are the 9, up to 9 are integers less than 10, but our definition says that greatest integer less than or equals to x. So here x is equals to 10. So to find the greatest integer function, we have to find the greatest integer less than or equals to x. So for x is equals to 10, the integers less than or equals to 10 are 8, 9, 10. So 10 is the greatest among all the integers which are less than or equals to 10. So greatest integer function of 10 or integral part of 10 is 10. But for 7.2, the integers less than 7.2 are 7, 6, 5, 4, 3, 2, 1, minus 1, minus 2. All are integers less than 7.2, less than or equals to 7.2. But greatest among all those integers is 7. So 7 is integral part of 7.2. That is 7 is integer in 7.2. So 7 is integral part of 7.2. This is second example. For example, if we take the third example as negative number, suppose negative of 4.5 minus 4.5. So to find the greatest integer function or integral part of x, that is integral part of minus 4.5, minus 4.5. So we have to find the, so first of all find the integers which are less than or equals to this number. So this number is a rational number, that is 4.5. So we are going to, here equal to condition is not going to hold. So integers, first of all we are going to find the integers less than 4.5. So minus 4 is less than 4.5, minus 5 is less than 4.5, minus 6, minus 7, all the integers which are less than 4.5, but the greatest among all the integers which are less than 4.5 is minus 4. So, one thing is must be in our mind that here numbers are increasing in order, here the numbers are in decreasing order. So, if we take the number suppose 2.5, so integer less than 2.5, here if we take 2.5, then integers less than 2.5 are 2, 1, 0, this minus 1, minus 2, all are integers. And for example, suppose if we take minus 1.5, then less integers, integers less than 1.5 are minus 2, minus 3. So, if we take less than, then we are going to in this direction. So, if we take the greatest integers among all those less integers, so for example, x is equals to minus 1.5, so these minus 2, minus 3, minus 4 are all less than 1 minus 1.5, but the greatest among them is minus 2. So, you can find in this manner. Now, we are going to take one theorem on this definition of greatest integer function. So, first theorem of our fourth chapter is similarly from the previous chapter we have seen that first theorem is just the properties 2 or 3, 5, 6 some properties of that function. So, here we are going to find the or derive or prove the 4, 5 properties of this greatest integer function. Statement of the theorem is let x and y be any real numbers, then first property is greatest integer function of x is less than or equals to x. This is by definition of greatest integer function. Greatest, this is just the definition, since integral part of x is greatest integer less than or equals to that number. This is just the greatest integer less than or equals to this x, which is strictly less than integral part of x plus 1, or in the first property x minus 1 is less than or equals to integral part of x is less than or equals to x, or this property first property can be written as 0 is less than or equals to x minus integral part of x is strictly less than 1. So, this is just the first property. So, 3 properties in first. Now, second, integral part of x is just the summation of 1 from 1 to x. This is just obvious result for any x greater than or equals to 0. Third property, integral part of x plus m is equals to integral part of x plus integral part of m. This property holds if m is an integer. Fourth property, integral part of x plus integral part of y is less than or equals to integral part of x plus y. Integral part of x plus integral part of y is less than or equals to integral part of x plus y, which is strictly less than or equals to which is less than or equals to integral part of x plus integral part of y plus 1. Fifth property, integral part of x plus integral part of minus x is either minus 1 or 0, if x, this integral part of x plus integral part of minus x is equals to minus 1. This is possible if x is not an integer, that is if x is some rational number, then integral part of that x plus integral part of minus x is equals to minus 1, and 0 is otherwise. If x is itself integer, suppose x is equals to 1 plus integral part of minus 1 is again minus 1. So, 1 plus minus 1 is 0. So, x is integer, then their integral part of x plus integral part of minus x is equals to 0. Sixth property, integral part of x by m is equals to integral part of x by m. is integral part of x by m is equals to integral part of x by m. This is possible if m is positive integer. If m is positive integer, m is positive integer. Seventh property, seventh and the last property of this theorem. Seventh property, minus of integral part of minus x, negation of integral part of minus x is least integer greater than or equals to x, greater than or equals to x, greater than or equals to x. Minus of minus x is least integer which is greater than or equals to x. So, we are going to prove these properties one by one. So, in the proof, first of all we have given that x and y be any two real numbers. So, we can express x and y is any real number. For example, if we take x is equals to 7, so we can write 7 this sorry for example x is equals to 7.2, then we can write 7.2 as 7 plus 0.2, 7 plus 0.2 is 7.2. So, we can write this number 7.2 as 7 plus 0.2. So, we can express this x as integral part of x, since 7 is integral part of x. So, we can express x as integral part of x plus some L. L is just the number which is less than or equals to 0 is less than or equals to that number is less than 1. So, that number L must be from 0 to 1. Similarly, we are going to express the y. Here we have given x belongs to R be a real number, be a real number. Therefore, this be any real number. Therefore, x can be written in the form integral part of x plus L, where the 0 is less than or equals to L is less than 1. For example, we have seen this example, that is x is equals to here 7.2. So, we can write this 7.2 as integral part of x plus 0.2, that is 7 plus 0.2. Integral part of 7.2 is 7 plus 0.2. So, L is equals to 0.2. 0.2 plus integral part of x is that x. So, we can express this x in this form. This is equation number suppose our star. This is we are going to use this equation in almost every property. Now, suppose this integral part is equals to n. We are going to take this integral part of x is equals to n for some cases. Therefore, we can express x as n plus L. Now, to prove the first property, our claim of the first property is integral part of x is less than or equals to x, which is strictly less than integral part of x plus 1. Our first claim is integral part of x is less than or equals to x, which is strictly less than integral part of x plus 1. This one side, that is the left hand side, x is greater than or equals to integral part of x, or integral part of x is less than or equals to x, is clearly by definition we can say that this is possible, since integral part of x is the greatest integer among all the integers which are less than or equals to x. So, this is obviously true, that is clearly integral part of x is less than or equals to x. This is by definition of greatest integer function. By definition of greatest integer function. This is one case. Now, we are going to prove x is strictly less than integral part of x plus 1. Since this L is less than 1, as this small l is less than 1. Now, if we add this integral part of x on both sides, then we get integral part of x plus L is less than integral part of x plus 1, and integral part of x plus L is x. So, our result is proved. Adding integral part of x on both sides, we get integral part of x. Adding integral part of x on both sides means on this equation integral part of x plus L is less than integral part of x plus 1, but by equation number star we have integral part of x plus L is equals to x. So, therefore, from equation star we can write this equation as x is less than integral part of x plus 1. Now, from this suppose equation number A, this is suppose equation number B, from equation B and A, that is combining equation A and B, we can write from equations A and B, we can write integral part of x is less than or equals to x, and this x is less than integral part of x plus 1. Hence, the first claim is proved. In the first property we have another two claims. So, in between them one of them is x minus 1 is less than or equals to integral part of x is less than or equals to x. So, next claim is integral part of x is integral part of x minus 1, next claim is x minus 1 is less than or equals to integral part of x is less than or equals to x. Now, clearly second condition is obvious because by definition of integral part. So, only we have to prove x minus 1 is less than or equals to integral part of x. So, step all right, clearly integral part of x is less than or equals to x. Now, we have to prove x minus 1 is less than or equals to integral part of x. We have x is equals to integral part of x plus L. So, as we have x is equals to integral part of x plus L, and we are going to prove x minus 1 is less than or equals to integral part of x. So, subtracting 1 from both sides, we will get x minus 1 is equals to something. So, subtracting 1, this 1 from both sides, we get x minus 1 is equals to integral part of x plus L minus 1. So, from this equation we can say that x minus 1 plus L minus 1, integral part of x plus L minus 1 is equals to x minus 1, but this L minus 1, our L is strictly less than 1. So, L minus 1 is clearly a negative number. So, integral part of x plus some negative number is equals to this term. This means that x minus 1 is less than this number integral part of x, because L is less than 1 and L minus 1 is clearly a negative number. So, adding negative number to this number or subtracting something from this x gives us x minus 1. Subtracting something from this integral part of x gives us x minus 1. This implies that x minus 1 is clearly less than integral part of x, because we have to subtract some term from this integral part of x. This gives x minus 1. So, clearly x minus 1 is less than or equals to integral part of x. So, this will give us, therefore, we can write x minus 1 is less than or equals to integral part of x. Reason behind this is L minus 1 is a negative number, L minus 1 is negative number. Therefore, we have this x minus 1 is less than or equals to integral part of x, and which is clearly less than or equals to x. Hence, second claim is proved. Now, the third claim in the first property is 0 is less than or equals to x minus integral part of x is less than 1. So, to prove this claim, we have x is equals to integral part of x plus L So we can rearrange this as, we have to prove 0 is less equal x minus integral part of x is less than 1. So first of all we are going to get this x minus integral part of x from this equation. So just subtracting integral part of x from both sides, or just sending this integral part of x here, we get x minus integral part of x is equals to L. So our L is the number between 0 to 1, as 0 is less than or equals to L is less than 1, that is this L is in between 0 to 1. We can write, and L is we have L is less than or equals to, 0 is less than or equals to L is less than 1, since this is from equation number star. Equation number star is this, 0 is less equal L is less than 1, and L is equals to this x minus integral part of x. So we can just rewrite this equation as 0 is less than, so putting L is equals to this value x minus integral part of x, we get our proof of the third claim. Now to prove second property. Second property is just obvious result. Clearly integral part of x is x, which is greatest integer less than or equals to x. So integral part of x is equals to 1 plus 1 plus 1 plus 1. This is x times. For example, we have seen this example here. Suppose x is equals to 7.2. So integral part of x is 7. So adding 1 7 times, we get 1 plus 1 plus 1 7 is equals to 7. So integral part of just this summation of 1 x times. This result is obvious. There is no need to prove anything. Just write this summation I running from 1 to x 1, that is I is stand for index. So just adding 1 x times, we get our result. For that x must be greater than 0. We are finding it for positive integer. Now the third claim is, that is third property is integral part of x plus m is equals to, third claim is, or third property is integral part of x plus m is equals to integral part of x plus integral part of m, and we have given m is an integer. This property is true for m is integer. So we have given m is integer, and we have to prove that integral part of x plus m is equals to integral part of x plus integral part of x plus integral part of m. So we have x is equals to integral part of x plus L, where L is in between 0 to 1. Now we are going to consider this left hand side, as x is equals to this. So x plus m will become integral part of x plus L plus m. Now we are going to take the integral part of both sides, that is integral part of x plus m is equals to integral part of this integral part of x plus L plus m. So we can write this as integral part of x, that is integral part of x is an integer. So their integral part is again integral part of x. Now m is also integer. So integral part of m is m, and L is in between 0 to 1. So integral part of that L is 0. So it will become integral part of x plus m. Hence we have integral part of x plus m is equals to integral part of x plus integral part of m. So here just make one correction, integral part of x plus m is equals to integral part of x plus m, not integral part of m. Also in this statement the correction, in the statement of this integral part of x plus m is integral part of x plus m if m is an integer. It is just one correction. So hence the proof of third property. Now fourth property, that is fourth claim is integral part of x plus integral part of y. This is claim, fourth claim. Integral part of x plus integral part of y is less than or equals to integral part of x plus y, which is less than or equals to integral part of x plus integral part of y plus 1. To prove this claim, we have x is any real number, similarly y is any real number. So, we have x is equals to integral part of x plus L. Similarly, we can write y is equals to integral part of y plus m. This L and m is again in between 0 to 1, as this x is in the form, y is again in this form. So, adding x and y, we get x plus y, and after that taking integral part of x plus y, right. So, therefore, x plus y will become integral part of x plus integral part of y plus L plus m. Now, taking integral part of x plus y, this is just the integral part of x plus integral part of y plus L plus m. So, integral part of x is here, this x integral part of x is integer. So, integral part of integer is again that integer itself plus this integral part of L plus m. Now, this L is in between 0 to 1, m is again in between 0 to 1, as this 0 is less equal, L is less than 1, and 0 is again less than or equals to m is less than 1. This will give L plus m is in between 0 to 1, sorry, 1 plus 1 is 2, 0 to 2. Therefore, the integral part of L plus m is less than or equals to 1. So, we can write this integral part of x plus y. Therefore, integral part of x plus y will be less than or equals to integral part of x as it is, integral part of y as it is. Just writing L plus m is less than or equals to integral part 1, integral part of L plus m is less than or equals to 1. We will get this inequality, integral part of x plus integral part of x plus y is less than or equals to integral part of x plus integral part of y plus 1. This less than or equals to sign comes here, the less than or equals to sign comes here, since integral part of x L plus m is less than or equals to 1. Here there are two possibilities for L plus m, either this L is equals to suppose 0.2 and this m is again equals to 0.2. So, 0.2 plus 0.2 is 0.4. So, integral part of 0.4 is 0. So, this L plus m is strictly less than 2. So, this L plus m may be less than 1. So, if this L plus m exceeds 1, that is, if suppose L is equals to 0.75 and m is again equals to 0.75, then L plus m is 1.5 and their integral part is 1. So, integral part of L plus m is less than or equals to 1. So, there are two possibilities, either 0 or 1. So, this integral part is less than or equals to 1. So, instead of this integral part, you will take less than or equals to 1. So, this integral part is less than or equals to 1. So, this equality becomes this. So, this is the right hand side of our claim, that is integral part of x plus y is less than or equals to this. So, this right hand side is proved. Now, to prove the left hand side, that is integral part of x plus integral part of y is less than or equals to integral part of x plus y. So, for that we can consider integral part of, from this equation we can write this. So, this from this equation we have integral part of x plus y is equals to integral part of x plus integral part of y plus something. So, we have to add this term in this integral part of x plus integral part of y will gives us integral part of x plus y. So, this is equation number capital A. Also, from equation A we have integral part of x plus y is equals to integral part of x plus integral part of y plus integral part of L plus m. This will give integral part of x plus integral part of y is less than or equals to integral part of x plus y. Since we have to add something, that is integral part of x plus integral part of y plus integral part of L plus m is equals to integral part of x plus y. So, we have to add this term in this addition gives us integral part of x plus y. So, integral part of x plus y is clearly greater than this addition. So, integral part of x plus integral part of y is less than or equals to this. Here less than or equals to sign appears here because integral part of x, so integral part of L plus m is either 0 or 1. So, from this and these equations, equation number suppose A, B, C and D, from equations C and D we can write integral part of x plus integral part of y is less than or equals to integral part of x plus y, and which is less than or equals to integral part of x plus integral part of y plus 1. Hence, the group of fourth property. So, remaining three properties we will see in our next lecture.